Good morning. Today I'm going to talk about my machine learning project, which focuses on predicting whether a person is diabetic or not using medical and demographic data. Diabetes is a serious and long-term health condition, and early detection can help people take preventive measures. In this project, I followed the complete machine learning pipeline, starting from data loading and pre-processing, then model training and evaluation, and finally deploying the model using gradient interface so it can be used by non-technical users. The main problem I addressed is that diabetes is often detected late. Because of this, there is a strong need for a simple, low-cost and non-invasive method that can help identify people who may be at risk of diabetes at an early age. To develop a machine learning model that can predict diabetes accurately, analyze which medical features contribute most to diabetic risk, create a user-friendly interface for an easy interaction. The dataset used in this project contains around 768 records and 9 columns. Out of these, 8 are inputs featured and 1 is the target variable. The target variable is called outcome, where 0 represents non-diabetic and 1 represents diabetic. The input feature include pregnancy, glucose, blood pressure, skin thickness, etc. The data was loaded from a CSV file and inspected for structure, missing values, and basic statistics. Okay, now let's talk about model development. For this project, I chose logistic regression as the main machine learning algorithm. I chose logistic regression because it is simple, efficient, and highly interpretable. If it allows me to understand how each feature influences the prediction through its coefficients, which is very important in healthcare-related applications. First, I separated the dataset into input features X and the target variable Y. Then the data was split into 80% training data and 20% testing data to evaluate the model on unseen data. Since logistic regression is sensitive to feature scale, I used a standard scaler to standardize the feature. The scaler was fitted only on the training data and then applied to test data to avoid the data leakage. Feature importance was analyzed using the logistic regression. The most influential feature were glucose, BML, age, like glucose, which was the strongest predictor, BML showing the link between body weight and diabetes, age, where higher age increases diabetic risk. These results align well with existing medical knowledge, which increases confidence in the model. The model achieved an overall accuracy of approximately 75% on the test dataset. The key evaluation metrics were accuracy, precision, recall, F1. Recall performed better on non-diabetic cases, whereas precision worked higher for non-diabetic cases than diabetic cases. The confusion matrix showed that the model correctly predicts most non-diabetic cases, but some diabetic cases were misclassified. This indicates that while the model performed well overall, there is still room for improvement in identifying diabetic cases. And for correlation heat map showed the strong relationships between glucose, BML, age, and diabetic outcome. The outcome distribution plot confirmed that the dataset is slightly imbalanced, which explains why recall for diabetic cases is lower. Overall, the model performs well for early diabetes detection, but can be improved for rarer diabetic cases in future. Let's go and speak about the gradient interface development. To make the model usable, In real-world scenarios, I developed a graduate interface. Interface allows users to input medical information such as pregnancy, glucose level, blood pressures, BMI, age, insulin. Once the user enters the value, the system instantly predicts whether the person is diabetic or non-diabetic, along with the probability of diabetes. Let's jump on the conclusion. To conclude, I successfully developed a simple, reliable, and interpretable machine learning model for predicting diabetes. Logistic regression proved to be effective and easy to explain, and the results matched medical research findings. For the future work, I would like to improve handling of class imbalance, tune model parameters further, test more advanced algorithms, and use a larger and more diverse dataset than this, and integrate the system into real-life healthcare platforms in future. Thank you for listening. Let me walk through this. I will explain my machine learning notebook step by step. The aim of this code is to build a logistic regression model that predicts whether a person is diabetic or not using medical data. I will start from importing the libraries, then loading and exploring datasets, pre-processing, model training, evaluation, and finally deploying the model of using a gradient interface. First, I imported all the required libraries. I used Panda, NumPy for data handling, and the numerical operations, Matplotlib, and Seaborn were used for data visualization. From scikit-learn, I imported tools for splitting data, scaling features, training the logistic regression model, and evaluating performance using metrics such as accuracy, precision, recall F1, and the confusion matrix. Finally, I imported Gradio to build an interactive user interface for real-time predictions. Step 2, In this step, I loaded the dataset using pd.read_csv. The dataset contains 760 rows and 9 columns. I printed the dataset and used head and tail to inspect the first and last few rows. I also checked the column names, shape, and general structure of the data. This helped me to confirm that the dataset was loaded correctly and that all the features were present. I used functions like data info and data describe to understand the dataset better. For this, I confirmed that all columns are numerical, there are no missing values. The dataset is clean and ready for pre-processing. This step is important to avoid errors later in the model training process. Next, I separated the dataset into input features and the target variable. The input features are all column except outcome, and the target variable is outcome, where 0 represents non-diabetic and 1 represents diabetic. This separation is necessary so the model knows what to learn from and what to predict. I then split the data into training and testing set using 80-20 split. This means 80% of the data is used to train the model and 20% is used to train it on unseen data. I also used a random state of 42 to ensure reproducibility. Since logistic regression is sensitive to feature scale, I applied standard scaler. The scaler was fitted only on the training data and then applied to both training and test sets. This avoids data leakage and ensures that all features contribute equally to the model. Here I created the logistic regression model with maxed around 1000 to ensure convergence. I then trained the model using the scale training data, and at this stage the model learns the relationship between the medical feature and the diabetes outcome. After training, I used the model to make predictions on the test dataset. These predictions are stored in ypredict and are later used for evaluating model performance. I evaluated the model using several metrics. The model achieved an accuracy of approximately 75%. I also generated a confusion matrix and a classification report. As from the result, you can see the model performs better on non-diabetic cases. It performs reasonably well on diabetic cases, but still has room for improvement. Using multiple metrics helps provide a balanced evaluation instead of relying only on accuracy. I tested the model using a sample new patient with the realistic medical values. The input was scaled using the same standard scaler, and the model predicted the patient as non-diabetic. This step demonstrates how the model can be used in real-world scenarios. I created summary tables to check missing values, which were 0 across all the column. Target distribution also. Target distribution showed a class imbalance with more non-diabetic cases than diabetic cases, which explains some of the evaluation results. I created an evaluation table showing accuracy, precision, recall, and F1 score in clean format. This makes the result easier to understand and to present it to someone. I plotted several charts to better understand the data and model behavior. A count plot showed the class imbalance. As for the correlation heat map, it highlighted strong relationship between glucose, BMI, age, and diabetes. And for confusion matrix heat map, it showed correct and incorrect predictions. This visualizing helped explain the model's strength and weakness clearly. I analyzed feature importance using logistic regression coefficients. The most influential features were glucose, BMI, age. This aligns well with medical research, which increases the trust in the model. Finally, I created a gradual interface user which can enter medical details such as glucose level, BMI, age, and other features. The input is scaled automatically, and the model predicts whether the person is diabetic or not, along with the probability. The interface makes the model easy to use for both healthcare professionals and non-technical users. I would like to conclude by saying this notebook demonstrates the full machine learning pipeline from data loading to deployment. The model performs well for early diabetes detection and can be further improved in future work. Thank you for listening.